Have you ever stopped to wonder what's actually holding up a massive cargo ship? Or how the brakes in your car can stop 2 tons of moving steel with just a light tap of your foot? Well, the answer is this invisible, super powerful, and honestly fascinating force that's all around us, and even inside us. It's a force that shapes our world in ways you probably never even thought about. So let's decode it.
So here's the big puzzle we're tackling today. It seems to defy logic, right? I mean, they're both made of steel, which is way denser than water, and yet one just sails along the surface, while the other sinks straight to the bottom. To solve this mystery, we've got to dive into the hidden world of fluid pressure.
All right, our investigation starts at square one, with the fundamental concept that makes everything else possible: pressure itself.
So, what exactly is pressure? Put simply, it's just force packed into a specific area. That formula, P equals F over A, that's the whole secret right there. It tells you it's not just about how hard you push, but how concentrated that push actually is.
See, the secret ingredient here is the area. Imagine you press your hand flat against a wall. Now, imagine using that exact same amount of force, but with just the tip of your finger. Your fingertip creates way more pressure because all that force is focused on one tiny spot. This one simple idea, man, it's the key to everything from hydraulic lifts to why a sharp knife cuts so well.
Now, in fluids, like water, this gets even more interesting. It's called hydrostatic pressure. You see, a fluid doesn't just push down, it pushes in all directions, up, down, sideways, you name it. And the deeper you go, the stronger that pressure gets, because you're literally holding up the weight of all the fluid above you.
Okay, so we've got the basics down. Now we get to our first big clue in this whole thing, a law that almost feels like magic. It's a way to multiply force using nothing but a bit of trapped fluid. This is Pascal's law. And what it basically means is that in a closed container, pressure isn't picky. If you push on a fluid in one spot, that exact same pressure is instantly felt everywhere inside that container. It just spreads out perfectly without losing any of its punch.
A hydraulic jack is the perfect way to see this in action. You apply a pretty small force to a small piston. That creates pressure in the oil inside. Then that pressure travels through the oil to a much larger piston. And because that same pressure is now pushing on a much bigger area, the force that comes out is huge. It's how a tiny push on a pedal can lift a car that weighs tons.
And this isn't some obscure physics principle, you guys. It is everywhere. Your car's brakes? They use it. That chair at the dentist's office that lifts you up so easily? Pascal's law. In hospitals, special mattresses use it to distribute a patient's weight to prevent sores. And get this, even before we're born, the amniotic fluid around a fetus uses this exact principle to protect it from any bumps or pressure from the outside world.
We've seen how pressure can literally multiply force. But now, let's get back to the heart of our mystery. It's time to uncover the secret of why some things float and other things sink.
And it all comes down to this one famous idea from Archimedes. When you put something in water, it has to move some of that water out of the way, right? It displaces it. Well, the secret is that the water pushes back with an upward force. We call it the buoyant force, that is exactly equal to the weight of the water that got pushed aside.
And just like that, our paradox is solved. The tiny steel nail, it's small and solid. It doesn't displace much water, so the upward push from the water is really weak, and it sinks. But the ship is a masterpiece of design. It's got this huge, hollow, bowl-shaped hull that displaces an absolutely enormous volume of water. And here's the kicker. The weight of all that displaced water is exactly the same as the weight of the ship. The upward buoyant force perfectly cancels out the ship's downward weight, and that right there is why it floats.
Okay, cool. But wait a minute. That brings up a whole new question, doesn't it? If a giant ship is designed specifically to float, how does something like a submarine decide to just sink? And more importantly, how does it come back up?
You see, a submarine is basically a master of buoyancy. It's a boat that can change its own weight whenever it wants. To dive, it opens these vents, and huge chambers called ballast tanks flood with seawater. This adds tons of weight, making the sub way heavier than the buoyant force pushing up on it, and down it goes. To come back to the surface, it uses tanks of compressed air to literally blast all that water out, making itself much, much lighter. The buoyant force takes over again, and up it rises.
So these big principles, hydrostatic pressure, Pascal's law, buoyancy, they're not just for giant ships and high-tech submarines. They are actively shaping our world in countless ways every single day.
Ever look at a massive dam, like the Hoover Dam? Notice how it's way, way thicker at the bottom than at the top? There's one simple reason for that. To handle the absolutely immense hydrostatic pressure that's pushing against it, which is always strongest way down at the bottom.
Or how about in a hospital? That simple IV bag is always hung high above the patient. Why? Because the height of the fluid creates just enough pressure to overcome the patient's own blood pressure, letting the medicine flow right into their vein. It's simple but brilliant.
And get this, even drinking with a straw is a game of pressure. You're not actually sucking the liquid up. What you're really doing is lowering the air pressure inside the straw. The normal atmospheric pressure outside, which is now higher, literally pushes the drink up the straw and into your mouth.
And you know that cuff the doctor wraps around your arm for your blood pressure? That's a direct application of fluid mechanics. It works by squeezing an artery with just enough pressure to stop the blood flow, and then measuring the pressure inside your body when the flow starts up again.
So, from engineering marvels floating on the sea to the simple act of taking a sip of water, this invisible force of fluid pressure is constantly at work all around us. Now that you know the secret, the real question is, where else are you going to see it in your world today?